Hello everyone and welcome back to Exam Ignite YouTube channel. This is Embedded System Design Module 3 of 6th semester BEC601 subject code. Here we are discussing the RTOS and IDE for an embedded system design chapter. In the textbook it is the 10th chapter. So we'll be focusing on the topics of operating system basics and types of operating system, task, process and threads, and thread preemption and preemption task scheduling techniques, task communication, task synchronization issues in that racing and deadlock, and integration and testing of embedded hardware and firmware, embedded system development environment and its block diagram. And also there are few questions in this module. So here I have prepared the notes by referring to the prescribed textbook in the syllabus, and also here you can see the topics that have been asked as a questions in the various question papers like model question paper, or in the June-July 25 question paper, or December 25 or Jan 26 question papers. So all those things I have mentioned here. You can keep it for your reference to know the weightage of the topics which are important and has to be focused while studying. So let's get started. So real-time operating system based embedded system design. So what is operating system? It's an access and bridge between the user applications and the underlying system resources through a set of system functionalities and services. So OS manages the system resources and makes them available to the user application, that is task, on a need basis. A normal computing system is a collection of different IO subsystems, working and storage memory. So, what is the primary function of the OS? It is to make the system convenient to use, organize, and manage the system resources efficiently and correctly. Now, this is an architecture here. This OS or architecture, the components in this operating system consist of: one is user application, kernel services, and underlying hardware. So these both are connected by an application programming interface, and this is connected by a device driver interface. So kernel services contain memory management, process management, time management, file system management, and input output system management. This is an important question. You can expect this. They will ask the architecture of OS. So we'll go in depth. Firstly, the kernel is the core of the operating system and is responsible for managing the system resources and communication among the hardware and other system services. So it acts as what? It acts as an abstraction layer between the system resources and user application. So kernel contains a set of system libraries and services. For general purpose OS, the kernel performs the first is the process management. It deals with the managing process or tasks like setting memory space, loading the process code into the memory, allocating the system resources, scheduling and managing the process execution, setting up and managing the process control block, and then inter-process communication and synchronization, process termination or deletion. All this are included. Second one is primary memory management. That is refers to RAM, volatile memory, where the process are loaded and shared data are stored. So the memory management unit of a kernel is responsible for keeping track of a memory used by each process. Allocating and deallocating the memory space on a need basis is a dynamic memory allocation. Next is file system management. A file is a collection of related information. A file may contain a process source code or an executable code, text file, image file, or a Word document or audio video files. So the file system management is responsible for its creation, deletion, and alteration of the files, directories, or saving them into the secondary memory, providing an automatic file space allocation based on the free space availability, providing a flexible naming convention for the files. So next is input-output system device management. Here the kernel is responsible for routing the input-output requests from the applications to the input-output devices. So here kernel maintains a list of all the available IO devices. So whenever a new device is installed, it updates the list. So handles this IO devices is done, handling of this is done through the device drivers, which are low-level system calls. Okay, next is systems secondary storage management. So it deals with managing the storage devices because primary memory is volatile. So secondary memory means it is stored in the disk, that is hard disk. A kernel performs disk storage allocation, disk scheduling, free disk space management, like that. Then protection systems, here in the modern OS, it supports multiple users with a different access permissions. So protection systems provide security policies to the restrict the access to the user data and the system resources. Next is interrupt handler. Here the kernel provides a mechanism for handling the external and internal interrupts. Next is kernel space and the user space. Kernel space means it's a program code corresponding to the kernel application services is stored in a contiguous area of a primary memory. It is protected from the unauthorized access by the users, and here the kernel application code usually remains in the main memory and it is not swapped out. Whereas the user space, it is user applications are loaded into a separate area of memory called as user space. User applications are executed in this memory space. So partition between the kernel space and the user space depends on the operating system. Okay, so the process of loading the code in and out of the memory between the primary and the secondary storage is called as swapping. So next comes the monolithic kernel and the microkernel. So this is a question. This was asked. This is the model question paper question. You need to write the difference between these. So based on the kernel design, it can be classified as two types. So first one is monolithic kernel architecture. Here all the kernels run inside a kernel space. All the kernel modules run in the same memory space under a single kernel thread. Advantage here is there is a tight internal integration which enables an effective utilization of the low-level hardware features. But what are the disadvantage here is failure in one kernel module may crash the entire application system. So that is what example you can use here Linux or MS-DOS like that. This is a monolithic kernel model. Next comes microkernel. Here in this architecture, only essential operating system services are included inside the kernel. Remaining services run as a servers in the user space. So essential services inside the microkernel like the memory management, process management, timer systems, interrupt handlers, only these things will be inside. Examples are Mash QNX and Minix 3. So this is a microkernel model. Next is the benefits of the microkernel then. Robustness and the configurability. It is suitable for the systems requiring high availability. Next is types of operating system. We are having two types. One is GPOS and another is RTOS. So GPOS is general purpose operating system where operating system deployed in the general computing systems. So here the kernel of the GPUs is more generalized and contains all kinds of services required for executing the generic applications. Characteristics here is they are often non-deterministic behavior. They introduce random delays. Application responsiveness may become slow at unexpected times. So used in the system where the deterministic timing behavior is not important. A personal computer or a desktop system is an example of this GPOS. So example of GPOS is Windows 10 or MS-DOS. Next comes real-time operating system. Here, this is not universal definition for real-time operating system, but in broad sense, you can say it implies to the deterministic timing behavior. Like it implements policies and rules concerning time-critical allocation of system resources. Like RTOS decides which application should run, in what order the task should be executed, and how much time should be allocated for each of the tasks. So the major feature is predictable performance can be expected. Example is Windows Embedded Compact QNX and Micro C or OS2 you can say. Next comes real-time kernel. Here, the kernel of the real-time operating system is called as a real-time kernel. Compared to the conventional OS kernel, so the RTOS kernel is highly specialized because it contains only a minimum set of services required for running user applications or tasks. So basic functions of this real-time is task or process management, scheduling, synchronization, error or exception handling, and then memory management, interrupt handling, time management can be expected. So each of them will be explaining. Task or process management means setting the memory space for the task, loading the task into memory, allocating the resources, setting up the task control block, and then the termination. So the task control block stores the information corresponding to that task. So what are the parameters that will be stored in the TCB or ID, its state, type, priority, context pointer, memory pointers, then resource pointers, then other parameters are all stored. Functions you can see here, it can create, it can delete, it can remove, then it can update. Like this, there are the tasks you can modify. Then comes the task or process scheduling. Here, task scheduling deals with sharing the CPU among the various tasks or processes. A kernel application is called scheduler, handles the task scheduling. So, scheduler is an algorithm that performs efficient task scheduling, ensures the deterministic behavior, decides execution order of the tasks. Next, task or process synchronization. This deals with the synchronizing the concurrent access to the resources, communication between the different tasks. It prevents the conflicts among the tasks while accessing shared resources. Error or exception handling means errors occurring during the execution or exceptions raised by the task. So this include insufficient memory or deadlocks or timeout conditions, missing deadlines, bus errors, divide by zero, unknown instruction executions. So next is deadlock. Example is deadlock and timeout. Deadlock in the kernel level exception and timeout is task level exception. Memory management is compared to the GPOS. Memory management in RTOS is slightly different because RTOS focuses on the deterministic timing behavior. So that uses block-based memory allocation instead of dynamic memory allocation. So next comes interrupt handling. In the interrupts provide real-time behavior to the systems. They inform the processor that an external device or the task needs an immediate CPU attention. So we are having two types. One is synchronous interrupts and asynchronous. In the synchronous, it occurs in a sync with a currently executing task. Examples is divide by zero or memory segmentation error. Like that, asynchronous occur independently of the current task. Time management, it provides precise timing reference for the application. RTOS use a high resolution real-time clock hardware timer. So the functions of the timer clock interrupt you can refer here. Next comes the hard real time. So systems that strictly adhere to the timing constraints are called hard real time. They must meet the deadline without any delay. So missing deadlines may cause a permanent data loss or irrecoverable system damage or safety hazards. So that is what about the hard real time. About the soft real time, in the hard real time example is airbag control system and anti-lock braking system. So in soft real time, it does not guarantee a strict deadline, but it will try its best to meet them at the required time. So that is called a soft real time system. Missing deadline is acceptable within the QoS limits, that is quality of service. So here example you can give as ATM machine and then audio video playback speed. Second topic is about the task, process and threads. So firstly, tasks. So the term task refers to something that needs to be done. So it can be defined as a program in execution along with the related information maintained by the operating system. So it is defined as a program in the execution along with the related information maintained by an operating system for that program. So task is only also known as a job in an operating system context. A program or a part of it in execution is also called a process. So thus the terms task, job, process generally refers to the same entity or it is used interchangeably. Next is process. A process is a program or part of it in execution. A process is also known as an instance of a program in execution. So multiple instances of the same program can be executed simultaneously. A process executes in a sequential manner. So then what is the structure of a process? So the concept of process enables the concurrent execution of the task, resulting in an efficient utilization of CPU and resources. It behaves like a virtual processor, holding a set of registers, process state information, program counter, stack memory, and code corresponding to process. So this is the structure of a process, and this is a memory organization of a process. So in the memory organization, you can see there is a stack memory downwards, data memory upwards growing. So data memory and the code memory. So next comes stack memory. Here it stores the temporary data, holds the local variables of the data, usually goes downwards. Data memory will go upwards. Code is nothing but about the program instruction. Now, process states and transition states. So the execution of a process from the creation to the termination is called as a process life cycle. So this is also an important question. You will be asking about the explain the process life cycle. So it process changes its states from the newly created states to terminated state through the different stages. So here we can observe firstly it is created, then there is an inception into the memory that is sent to the memory, it is ready for the execution, then it is scheduled for the execution, then it starts running. Once the execution is completed, it gets completed. So running, if there is an interrupt or preempted, then it will go back to ready, or there is a blockage, it will wait for the input output waiting for the shared resource. Once it is completed, the shared resource is acquired, it gets back to the ready state. So you have to explain the each state, like what is about creation, that is initiate the start process, operating system recognizes the process, resource gets allocated. In the ready, process is loaded into the memory waiting for the CPU allocation, and it is placed in the ready list queue. In the running state, the instructions are currently executing and CPU is allocated. In the block or wait stage, when the process execution is temporarily suspended, it waits for an input output event, or it's wait for an user input, or waits for the shared resource. Then completed state means process execution completes the execution, terminates normally. So state transition, now you have to explain the transition states, like from ready to running, running to blocked, running to completed, and blocked to ready. So this was all about that. Now next comes the process management. So here it deals with the creation of process, setting the memory space, loading the process into code. Then there is a resource allocation, creating of PCB, then process termination or deletion. Next is thread. Thread means it is a primitive that can execute code. It is a single sequential flow of a control within a process is known as a lightweight process. So a process may contain multiple threads. So threads belong to a same process, share the address space, data memory, code memory, heap memory. However, each thread maintains its own thread status, that is CPU register value or program counter and stack. So memory organization of a process and its associated threads is shown here. The concept of multi-threading. A process may involve multiple operations. So, if all the operations are executed serially, CPU utilization becomes inefficient. Suppose, let us consider an example where a process is waiting for a user input. If only one sequential execution exists, then CPU enters the wait state. Process execution is pause. So instead, if the process is divided into multiple threads, one thread can wait for the input output, other will continue the execution. So thus there is a CPU utilization improvement. So this is the process of multi-threading. Advantages: better memory utilization, faster execution, and efficient CPU utilization. Thread standards, they define the mechanism of the thread creation and management. So these standards are provided through a thread class libraries. POSIX threads, it means portable operating system interface. We are having two, one is .4 and .4a. It is real-time extension and this is thread extension. So POSIX standard thread library is called as pthreads. It provides functions for the thread creation, thread management in C language. Thread standards, that is a continuation of that. Here we are having pthread join primitive. Here it is used to block the current thread and wait until the completion of another thread, like this. So multi-thread application using pthread, that is a multi-thread application can be designed to print. For example, hello, I'm in main thread from the main thread, and hello, I'm a new thread from the new thread. So both these messages are printed 5 times each using this instruction. So the execution output helps to understand the thread switching behavior. So here you can observe the output sequence may not be the same every time because the scheduling depends on the operating system. The switching between the main and the child threads depends on the thread scheduling policy. Next is termination. How do you terminate? Naturally, when it returns the control to main, forced by using this functions. Next is Win32 thread. This is supported by a different version of Windows OS. So this Win32 API provides a thread creation and management functions using this function. Here we have to know the important parameters where we specify the function to be executed by thread, pass the application defined value to the thread routine. So these are some of that. So important Win32 thread APIs were listed in the textbook I have given here. Another example is Win32 multi-thread applications. It is designed to create a counter in the main thread, create another counter in the child thread. So count from 0 to 10 after a delay of 500 milliseconds between prints. So program will use these two functions and output shows that main thread and the child thread execute alternatively. Next is the Java threads. So this is the output of a Java thread. It is pasted above. The Java provides thread support through the thread class present in the package. So thread support must be imported before the use. So two types, one is extending thread class and another one is implementing an interface. When a thread class is extended, methods and variables of a parent class are inherited. Run method is overridden, and run method contains a task to be executed by the thread. The method is given here, and the yield method or the sleep method or wait method, thread end state, and summaries of all the thread libraries that we have studied, and the thread preemption. So thread preemption is an act of temporarily stopping the currently running thread. So it depends completely on the OS. So it is performed to share the CPU time among all the threads. So switching between the executions between the threads is called as in thread context switching. It depends on the OS scheduler and type of thread. Again, it is classified into user level thread and kernel level thread. In the user level, it does not have an OS support, exist only in the current running process. Here, user threads are non-preemptive at the thread level from an OS perspective. So, but in the kernel system level thread, it is our individual execution units treated by OS as a separate threads, and threads are preemptive. So differences, you can note it down, the difference between the user level and the kernel level threads. So thread binding models, we are having many to one model where many levels of threads are mapped to one kernel thread, and one to one model, here one kernel, it is associated with one kernel system or level threads, has a direct kernel support. Many to many, here many user level threads are mapped to many kernel level threads. So, and also this is an important part where you need to know the difference between the thread versus process. Thread is a single unit of execution and a part of process. Process is a program in execution containing one or more threads. Does not have its own data or heap memory, but here it has its own code memory, data memory, and stack memory. Thread shares a memory with other threads of the same process. Process has a separate memory organization. Thread cannot live independently. Process can at least contains at least one thread. And then multiple threads can exist in one process, here one or more threads. Then threads share common data memory or heap memory. Here there is an inside process share code, data, and heap memory. Threads are inexpensive, processes are expensive. Context switching is fast and expensive, here complex and slower. Then it is if the thread expires, stack is reclaimed by the process. If the process dies, all the resources and threads are reclaimed by the OS. That is a main key difference between thread and the process. Next is the preemptive scheduling, where we'll be discussing this in the module 3 part 2 video. So thank you for watching. Please do like, share, and subscribe to Exam Ignite.